the application of these two functions is more apparent in this example. So this is again using this is the green function of just the Laplace equation, right? So the left hand side is the Laplacian in cylindrical coordinate, and it's right out in your notation of your textbook, which is a little bit non-conventional. So it basically have this index 1 and 2 for the two coordinate dependency on the green function. What one is the so R sub 1 is the coordinate of the first coordinate R sub 1, and this is the modified Bessel. Now this is the Laplacian equation, Laplace equation. So in cylindrical coordinate, right? 1 square, 1 square plus y square plus also square plus z square, and you want to find the green function that depends on two coordinates, R sub 1, R sub 2. And the right hand side is the delta function. 1 is R2. You want to find the green function. And so this is like free space green function. So basically that include all space has no boundary except the infinity. So include the origin and infinity. And that is the green function. But in cylindrical coordinate, but if in coordinate-free system, we already know what the green function, right? You remember the green function for that, the Laplacian, without the using coordinate system. What is that? It's like solving the solving the point charge, right? Yeah. The potential of a point charge. So if you have a point charge at for some of those of you that are taking E&M, so you say a point charge at R sub 1, you want to find the potential at R sub 2, right? Then there's a distance between R sub 1 and R sub 2 is R sub 1 minus R sub 2 to the absolute value, right? And the potential here, or whatever you want to use the symbol, and that will basically of the same form of the green function for this case. In the coordinate-free, what is LS proportional? What is phi proportional? You remember, those of you that taking E&M over here, what is the potential? Yeah, 1 by the distance, right? So it's 1 by this distance. Although in this case, probably you have this 1/4 pi factor because it's defined differently. So you probably will have 1/4 pi factor. But anyway, that's a coordinate-free green function. So this green function is really simple, but sometimes it's convenient to separate that and expand that in separable solution in different coordinate systems. So, and one of the possibilities is use a cylindrical coordinate, and that will involve either Bessel function, either J or J or I and K. So you can use the radial part using the Bessel function, and because you involve the origin, that you only have J for that one, or you want to use modified Bessel function for the radial part, and then the difference is that the Z part would be different. And I think we're out of time. Just write down the equation, what we want to do, and then maybe next time we'll go through that, finish this derivation. I mean, it's a little bit instructive to finish this derivation. Some of you probably seen that in E&M, but we'll do it again, and because it's illustrative to illustrate the point that why we have two functions I and k, and why and when you want to use I and when you want to use k. Okay, so we'll go for that next Monday. Then let's finish. I think we are in the example. We just started it. So now we start from. So we discussed last time the meaning for finding the green function, that is geometrical meaning. Now we just start deriving this green function, and solving this equation. This is 14.114. We have the operator on the coordinate 1, so partial row 1, where the row 1, so 1, rows 1 square, partial square, square, partial by 1 square, partial c square. We operate on the g function. The green function has two position vector r sub 1 and r sub 2, and this is operated on the coordinates of the first position vector. And the right-hand side is the delta function, which is the three-dimensional delta function, delta r sub 1 minus r sub 2. In coordinate, it should be like this. There's a 1 over r sub 1. There's apparently there's a okay. So r sub 1 instead of r sub 1 square. In your textbook is, do you have r sub 1 square in the denominator? You don't have. How about this? It should be r sub 1. I mean, you can always add another r, another row. I mean, because it has a delta function, but judging from the result that finally obtained in this example, this should be this r sub 1, not r sub 1 square. And the delta function, this is a delta function, three-dimensional delta function in coordinate form. And I'm saying that this is defined as the three-dimensional delta function. Right, and you have a suggestion how you confirm this is a three-dimensional delta function, how this is the correct form. Any suggestion? I'm saying this should be the form, but how do you know this is the form? Anyway, any suggestion for a three-dimensional delta function? How do you check it? Like you forget about the form and then you write down here, like the textbook I just mentioned, there's a square which is not correct. There should not be a square. It should be just one of those. But they say you forget exactly what it is, and then we want to know what should be the form, and how do you check that, confirm the correct form? Say that again? Dimension, yeah, that's good. That's good. Yeah, that's one way. So the three-dimensional delta function is basically a density. So it has a dimension 1 over length cubed, right? That's the density dimension. Each delta function is has the dimension of the inverse of its argument. So this one has a 1 over rho. There's a 1 over rho. There's a 1 over z. So altogether you have a correct density square. But the dimension will fix you up to a point, but you say you can always multiply by a dimensionless constant, still give you the same dimension, but how do you fix the exact form of the delta function? you forget about exactly the form, and then you write, it gets a form like this. You check whether this is correct. How do you do that? Anyone? Derivative? Yeah, integrate. Yeah, exactly. That's because the delta function is by the definition. So if you integrate this delta function, integrate one of the coordinates, dq of r, dq1 or I'm saying what symbol I should use, dq of x cosines r1. Sometimes people use the vector r1 to represent the volume integral. That's fine. Yeah, you include that this one, this two. If you have over volume, so you have if this is the R1 space, this is R1 space, and you have a vector R2 here. If you have a volume that include this point R2, then if the R2 inside V, then this should be 1, and outside of it should be 0, right? That's the definition. And basically, you can, after you do that, you can shift your coordinate system to set R2 to be the origin. So basically, you can cancel all the 2, become set it to 0. Right? And that is one way to do it. But to fix the form, now you need to know the volume element. The volume element is in cylindrical coordinates is R, dr, d rho, dz, d phi, right? So that's the volume element. And actually, I should say rho is the correct one. Rho, d rho, dz, d phi, right? And now you multiply to this, that you require a rho to cancel the rho in the denominator. And those delta function, you just use the property of delta function. You integrate rho of rho. This delta function will give you 1. This phi, integrate phi will give you 1. dc over this one give you 1. If the volume include at this point, right? And therefore, that's the correct way. Instead of one over r squared, if you have 1 over r squared, you integrate, you get extra 1 over r. In this case, 1 over r2, and that is not correct. Okay, so that's how you do it. So sometimes just try to figure it out. If you forget something, try to find some way to figure things out, especially when you're taking the exam, right? And now we continue, and the process is basically doing an expansion in the orthonormal basis. Doesn't have to be normal at orthogonal basis. So in this case, we want to expand the phi and z delta function in orthogonal basis, and then leave a 1D ODE for the rest of the green function. When we do the same thing for the capital G, and then after the expansion is like a separable solution. The radial part will have satisfy a ODE that involve a delta function and a rho. Okay, so that's the process. And for phi, it's easier if you are including all the azimuthal angle. So that is just Fourier series. You can say it's a Fourier series expansion of the delta function, or another way to look at it is a completeness condition of the Fourier series. So the delta phi, so delta phi 1 minus phi 2 should be just sum of all the integer in the usually take positive and negative integer, and then that e to the im 1 minus phi 2, and need to normalize it with 1 over 2 pi, and so that's the completeness I mean, you can check this in two ways. You look at the completeness condition, or you just regard this as a function that you want to do a Fourier series expansion. Fourier series expansion in the period of 2 pi, and then the n of the coefficient will be what you want. Once you put in the coefficient, that is the Fourier series expansion. Okay, so that's this part. And the z part, now you have a choice. I mean, if you have whether you want to do I should say after this part, there's a choice between rho and z. So because this is basically the Laplace equation. This is the green function for Laplace equation. For Laplace equation, so you cannot have all 3 dimensions have an oscillatory component. So so what you, at least for this, using this method, so you have a choice. Either you use an oscillatory function like sine or cosine for the z part, and then the rho part will become non-oscillatory. In that case, we'll get the modified Bessel equation. So that's what we'll do. Another way to do it is using exponential function in z, and then oscillatory function in rho, and in the rho factor. In that case, the rho part will give you Bessel equation, and most likely you need to do a expansion, just like the phi, using the Bessel function as your orthogonal basis to expand this delta function and then solve the equation for the z part using exponential function. And that's another way to do it, but we'll do it the first way. So assuming that the delta z part is oscillatory, basically now it becomes a Fourier transform instead of Fourier series. So in that case, that is also like what we call the completeness condition. But this is Fourier series, so it's is 1 minus e sub 2 and dk. Okay, you remember this one? I actually mentioned a few times. This is an important equation. This again, it is like doing a Fourier transform of the delta function. You can look at it that way, although it's a little bit mathematically it's not very rigorous. But anyway, that's the relation. And so you can leave it like that, or like your textbook, you use the symmetric property of this, the integram, because the exponential function become cosine and sine, right? And cosine is even function, sine is an odd function. You integrate k from -infinity to infinity. The odd function does not contribute to cancel the odd function. You just keep the even function and integrate from 0 to infinity and multiply by a factor of 2. Okay, so that becomes whatever pi infinity cosine of a e sub 1 minus e sub 2 dk. It's okay. So that's just even and odd. It doesn't have to. When we do that, there's a slight difference because the argument of the Bessel function later will have a argument k times rho. If you use this part, you have a negative k, which is fine. You can extend your argument of the Bessel function to negative value. That's no problem. But using this form, then the argument of the Bessel function becomes always positive, because rho is always positive. So if you use this, k is also always positive. Then you don't need to worry about the positive or negative argument for the Bessel function. Okay, so that's this form. I mean, that's the similar thing in here, m. So because you use m, because this is the completeness, so you use all integer. If for negative integer, the Bessel function will be a negative order. but that is also fine. So we know that for integer order, the Bessel function, the two Bessel function, say like I sub m and I sub minus m, they're actually the same. So, so that doesn't matter as long as you just apply the correct relationship between the negative order and the positive order. Is that okay? So up to here. So that is you put this 2 into this here, this 2, right? And you do the same thing for G, this capital G, but write it as I should say R2 as a expansion with an unknown radial factor. So basically you keep all the same normalization, yet there's a 1/2 pi, there's 1/2 pi, so 1/2 pi square. Now you have a summation of m and integration of k. And you have all these factors in the im, y1 minus y2, and then cosine of c sub 1 minus c sub 2. But all these are the factor in expansion, but then finally you have this g, and the textbook notation is g sub m. It depends on m and k. It depends on k, and also all these two coordinates. So rho sub 1 and rho sub 2. The other dependency are on and here, so phi and z. Right? And, all right, so that's the expansion. So, and so the rest is to solve this little g sub m. And what we do is just substitute this into the left hand side, right? The two brackets are not the same. Right, this into here and this two into there. And the process is like what we did for the separable solution. And you can go through the process, but if you just want to save some time, you just look at the dependency. So if you substitute this into here, the phi part will pull out minus m squared because this operates on this factor, right? Pull out minus m squared, so it becomes minus m squared divided by rho 1 squared. Okay, so that's a negative m squared. And for the z derivative, you operate on the cosine. The second derivative gives exactly the cosine, but a negative sign, right? And then the pull out a k squared in this case, because this is c sub 1. Derivative over c sub 1, so pull out minus k squared. Okay, so altogether, this have a minus m squared over rho sub 1 squared and minus k squared. Right? And then everything, and then these two derivative on the letter g, everything is operate on this two. It's like a differential operator now operate on this little g, but I substitute this one to minus m squared over 1 squared. This one is minus k squared. Is it okay? And then operate on the little g. And then you identify that part as the differential operator of the modified Bessel equation. Okay, so that if the right hand side is 0, the solution will be modified Bessel function. Okay, and the right hand side is the rest. Right, after you have all this, the rest is 1/4 rho sub 1 and delta function. The other two are just the rest which you take it out because this is an equation that is using orthogonal basis. So if the equation in the expansion equals to each other, then the argument, the rest of the coefficient must be equals to each other. So you just forget about all this summation and integration. Just write down the operation on G. It's okay. So that is what we'll do. And let's this, well, let's just write it down here, so because eventually I need some space. So basically now just write out the equation. So partial square, partial rho 1 square plus over rho 1, partial rho 1. Now minus, you have a k, m square, rho 1 square plus k square. So that's the differential operator on G. That depends on. Now the right hand side is the rest is rows of 1. So that would be the equation. And again, there's another typo in equation 14.116. The textbook missing one of the rows of 1. To make it, and you can again check the dimension. This is the textbook, the dimension is not correct. After you substitute the solution, the dimension is not correct. So there's one voice at 1. Okay, so that is the equation. That's the ODE, right? And now to solve for this, you apply the argument that if the right hand side is 0, so if rho 1 not exactly equals rho 2, then the delta function is 0. Then this is a modified Bessel equation. The solution is the modified Bessel function. Okay, so now we need to decide the form of the delta, the Bessel function we use. Okay, and now what we do is we already done this, so we can erase this here. Okay, so we now this piece of m is equals to, let's just write down the argument. K was, okay, so there are two cases. One is the rho 1 like less than rho 2. The other is the opposite, rho 1 with the rho 2. So for both cases, it's not equals. The two are not equals. So the right hand side is 0. So the solution for rho 1 is modified Bessel function. Now you pay attention to this two inequality. So if rho 1 is less than rho 2, then this means because rho is from 0 to infinity, that's the coordinate, right? The radial coordinate. So this can include rho 1 equals to 0. And in that case, you don't want to include all the k, in this case of m, because the m is the order. M is the order here, right? So you want to include the case of m because all the case of m's are singular at the 0 argument. So you don't want to have the case of m, so you have I sub m. And k equals 1. Okay, so this is basically the most important part during the derivation is to decide what what modified Bessel function you want to use, because that will set up whether you get the correct form or not, right? So that's for this part you get I sub m, and for the other case, rho 1 is greater than rho 2, so it can go to infinity. And now the other consideration is all the I sub m are singular or exponentially large at infinity. So the asymptotic. So although we haven't done that yet, that's the next section. But we already argued that that should be the case. I sub m's are singular, but k sub m's are, we define k or this k to be exponentially small. That's what we set up to do, and we'll show that in the next section. So this means for the second case, you have k sub m, k sub 1. That's okay. So that's that's part of it. I'm leaving some space at other part because we want to impose other condition. The other condition is this little g will need to be continuous at rho sub 1 equals rho sub 2. So the 2 will be the same, right? We want to do that. Okay, so that's the condition we impose on the Green function, right? And the continuity has some physical meaning. So you just like last time I mentioned that this Green function is like the potential, electric potential for like a point charge at rho sub 2. You want to find a electric potential at rho sub 1, r sub 1, or point charge at r sub 2. That's the potential. So and the potential, if the potential is discontinuous, and you get the electric field by taking the derivative of the potential. If it discontinuous, the electric field is infinitely large. You don't want that, so you want to keep it physical. So the G will be continuous at rho sub 1 equals to rho sub 2. Right? The function itself is continuous, but the next step will show that the derivative is not continuous. Okay, so we want to one simple way to make it symmetric or make it continuous is to make this two parts symmetric between rho sub 1 and rho sub 2, because you multiply k sub m. Because this is the functional form for rho sub 1 that satisfies the modified Bessel equation. It can multiply by a coefficient that is a solution of k and rho sub 2. So that is allowed. So multiply km k sub rho 2, k times rho sub 2, and this for this part multiply I sub m with rho sub 1. Right? If we do that, then when rho 1 equals to rho 2, then the 2 will be the same, right? That maintain that it's continuous, but that's up to this up to a coefficient. Textbook didn't have that. I'm just write down the coefficient. This coefficient should depend on the order, and possibly depends on k, because these are the coordinate dependencies, so it also can depend on k. It depends on m, k, and most of those. So it can depend on k if you want. Put it like that. And they multiply the same coefficient. Okay, so all right. So that's the form of the Green function. We are almost there. So the last step is to fix this coefficient. Okay, the last step. And to do that, we go back to this ODE for G sub n, little g sub n. And the common trick is to integrate both the left-hand side and right-hand side over a little range. So this is integrated over because all these are differential operator of rho sub 1. You integrate rho sub 1 around rho sub 2, basically integrate. So this symbolically, right? Just integrate both sides. Do I have space here? A little bit of space. Integrate these rho sub 1 and rho sub 2 minus a little bit. Rho sub 2 plus a little bit, and eventually we let this range go to 0. Okay, but you just the sandwich this rho sub 2 with a little range. Okay, and then the right-hand side is easy because by this design, so this integration over the delta function will give you 1, and because it's actually a function, the right-hand side should give you 1 over rho sub 2, right? So that's fine. We know that now. Let's just write. So the right-hand side will be, after you do this integration, is 1 over volts of 2. Okay. And now the left-hand side, there are 3 terms. Start from the last term, easiest because everything's normal. This is just regular function. And the G is also regular. G is not singular at any location. We want it to be physical. You don't want an infinite green function. So this integrate over a infinitesimal range will be 0 because any regular function that's not singular integrate a range that tends to 0. That integration will be 0. So that integration, the third part will be 0. Okay, that's the first argument. You can accept that, right? so that's the easiest part because everything is regular. Now the second part is integrate over this little range, but there's a derivative here, derivative of G over rho sub 1. And over this little range, this rho sub 1 basically is a constant. When treated like the constant is rho sub 2 because you integrate rho sub 2 range around rho sub 2, this infinitesimal range around rho sub 2. So that's, you can set that as the rho sub 2, but then this becomes a total derivative, right? Total derivative of G. So this part, the integration of this part becomes G sub m evaluated at the upper limit and lower limit, which is this one and that one. But then the upper limit and both lower limit means the G at for these 2 cases around rho 1 close to rho sub 2, right? But then we impose the condition that they are continuous, that the 2 sides are continuous over this the point rho sub 1 equals to rho sub 2. They formally write exactly continuous. So this integration, the subtracting the upper limit and the lower limit will be 0 because it is symmetric. It's okay. So that part, the second part also not contribute. Now the third part, actually the first one, the last part that we consider is the second derivative. So the same consideration means that this is also G sub m, also rho sub 1, evaluate at the upper limit is rho sub 2 plus a little bit, and lower limit is rho sub 2 minus a little bit. That's okay. So integrating this term will give you this one. Okay, you can accept that, right? Okay. Now this one is not continuous. This derivative, because we have 2 cases over these two the upper limit, lower limit. We are using these 2, and they are not the same. But after you take the derivative, they're not the same. Okay, and yeah, we want to write it. Hopefully we have enough space. Okay. Yeah, the upper limit is rho sub 1 equals to rho sub 2 plus something. So rho sub 1 is larger than rho sub 2 because this is a positive value. So rho sub, so this the second case. And so we take the derivative with respect to rho sub 1, and then finally set rho sub 1 equals to rho sub 2. That's okay. So the upper limit. So we take the derivative of this one, the k. So when you take the derivative, you take the derivative of the function, which give you k m pi, and then take the derivative over the argument, will give you a k, a factor of k. So you have a factor of k, and you will see that both will have a c sub m out. Okay, so you have km pi. And finally, evaluate rho sub 1 equals to rho sub 2. And then let's just move this part to the other side. I sub m k sub rho sub 2. Okay, so that's the upper limit. And finally, that equals to 1 over rho sub 2. And now the lower limit is rho sub 1 is rho sub 2 minus something. The rho sub 1 is less than rho sub 2, which is this part. You take the derivative over the I function instead. So the same consideration is minus, you have I sub m pi k rho sub 2 minus times k sub m k rho sub 2. Okay, so that is all the form. Now you can identify this as, you've seen this before. What is the square bracket? You've seen this before. Well, in a few chapters, the Wronskian, right? This is the Wronskian. This is the Wronskian between the. This is continue here. Let's continue here. So this is k sub c sub m. It's the Wronskian between I sub m and k sub m. What's the rho sub 2? K sub m. V sub 2. And okay, and we already discussed the Wronskian of Bessel function and argued that what you should remember what is the Wronskian dependence of the Bessel function. It must be 1 by x, 1 by the argument. So it must have an argument. This Wronskian must have the form of a certain constant divided by k sub rho sub 2. So you get the rho sub 2 dependency correctly. So you need the rho sub 2 to cancel the right hand side. But we still need to determine the exact form, because it's the one other than the one over the argument. You still have the coefficients. So you need to fix the coefficient in order to get this case c sub m correctly. Now you can either look that up or I mean, because of the form, you can evaluate this Wronskian at any values of k times rho sub 2. And usually you either evaluate at the close to 0, then you can use the power series expansion for I sub m and k sub m to evaluate that. That's one choice. Another choice is let the argument goes to infinity and use the asymptotic expansion to evaluate that. Either way is fine. I tend to think the asymptotic value is a little bit easier, right? Because although we haven't done that before. I mean, haven't divided this asymptotic expression. That's the next section. But let's just write out the answer. Look up the I and k, because they are not the same, so you need to be a little careful. And then you only need the leading order. You don't want all the complicated. You don't want to have too many series, because you can always take it as large as possible. Then you keep only the leading order. So I sub m k rho 2 at infinity. Okay, rho 2 goes to infinity. It goes to 1 over 2 pi. The argument is k rho sub 2 exponential large exponential function k rho sub 2. Okay, that's I sub m. And k sub m would be, I'm just looking at the next section, the expression in the next section. K sub m. Again, the large argument will be square root of pi over 2x, which is the argument k sub rho sub 2, and exponential function minus k rho sub 2. Okay, so you look that up. That's the form. And now we need the I pi and k pi. right? And remember the pioneer over the argument, over the whole argument, right? So let's just write it out. And because of we're taking the limit of that the argument is extremely large, actually take the limit is to infinity. Then when you take the derivative, we don't need to take the derivative over this this coefficient, that square root dependency, because taking the square of dependency will give you an extra 1 over rho, 1 over rho sub 2, right? That is a higher order. Let it go to 0. You only need to take the derivative over the exponential function. Okay, so let's see, I sub m pi. We'll go, so let's save some writing. We'll go to just when you take the derivatives, exponential give you exponential function, but then the derivative over the argument give you extra k. So you can write it as k times, this k times I sub m. Right? And then k sub m pi will give you, and that derivative give you minus k. Okay, so now we have all this. So this k sub m power of a minus k, right? Power of minus k. I should say. Yeah, we already take the, yeah, wait, this is I sub m. You probably don't need the k because I sub m is taking the argument. So we treat everything as an argument. So actually, this is the, actually, we don't actually need the k. Just put a negative sign. Yeah, it's not the derivative over rho. It's direct derivative over the argument. So that's just I sub m. This is minus k sub m. Right, and then so that km is minus. There's a minus sign. This one has the positive sign. So the both term actually is the same. It's the product of the two. The product of the two, and then so you have a factor of 2, and then a negative sign. So let's now we are really on our space. Let's just write it here. Okay, let's evaluate that. So you have k times c sub m, and remember you have a negative sign, and then a factor of 2, and the product of the 2. And take the product of the 2, the exponential function cancel, and the pi cancel. This is in the denominator, this is numerator, pi cancel. Only not cancel is 2k times rho sub 2. And both are in the square root, so you just get 1 over 2k rho sub 2. Okay, and 2 now to cancel, k cancel. Right, so this is equals to minus c sub m over rho sub 2, and equals to 1 over rho sub 2 by c sub m equals to minus 1. Okay, so now we fix everything. Go back to here. Now we can just write down our answer. Thank you. Okay, so that's the form of the g sub m, and then once you have the g sub m, you put it back to this expression for the capital G. You put this into here, then the capital G will be given by this form. So that should be the answer. So a little bit long derivation, but it's straightforward. And one final notation is the final simplification using some notation is to use this minus, because this is rho 1 less than rho 2. You can change this to a rho smaller. rho larger. Yeah, using this subscript of the lower sign, smaller sign, and larger sign, and to indicate this, so this rho smaller or larger is just it's just comparing rows of 1 and rows of 2. So whichever is smaller, go into the smaller sign. Whichever is larger, go into the larger sign. So in this case, for the first case, this is 1, rows of 1, this is rows of 2. In the second case, this is rows of 2, this is rows of 1. Okay, yeah. I can figure out this notation, this greater and smaller notation. So that's the answer. All right. That's the derivation, and the whole derivation, of course, is, I mean, it's important because it's the same method applied to derivation of the green function, or may not be this Laplace equation, maybe other similar equation, the Helmholtz equation, and whatever. So you can use the similar method. And yeah, the second thing to learn about is how to choose the modified Bessel function to use. One is singular at the origin, the other is singular at the infinity. So you need to use accordingly. Okay, so that's this discussion.